the first slot of the morning of the last day after the dinner. Okay. I want to keep track of the time because I realize that it is quite a long story to be told in half an hour, but let's see. Okay. This work is about coherence and its characterization beyond its bare quantification. Okay, so some examples of these are genuine multi-level coherence, imaginarity, quantum state texture, and this present work that I called coherence dispersion. So just a few facts. Coherence is a basis-dependent resource, and two of the most common ways to quantify it are through the L1 norm of coherence. So this prime here is just to tell you that we are summing the off-diagonal elements, okay? So A different from J. And also there is an entropy that translates a property of coherence only. This is called the relative entropy of coherence. And you just take an arbitrary state and make all off-diagonal elements 0, and then you take the difference between the von Neumann entropy of this incoherent state minus the von Neumann entropy of the original state. Okay, so this clearly is related only to coherence, because here you have the same diagonal elements here and here, but one has no coherences and the other generally does. Okay, we will need this later. So let's look at a general density matrix as a table of numbers. Okay, so those green numbers are real valued and they are a probability distribution. So they have a very different nature as compared to those orange numbers. They may be complex and so on. So I'm going to do a very simple exercise. I will look for, of course, you have to comply with this. And the exercise I want to do is just to consider these two sets separately and calculate very simple statistical properties, meaning average and variance. Okay, so for instance, for the populations, what is the average? Well, since the trace has to be 1, the average is 1 over d, which is the number of terms. Okay, you have d diagonal elements. So there's no freedom at all for the average of the populations. It is 1 over d, and this is completely equivalent to saying that the trace is 1. Okay. What about okay? So if you calculate the average of any set of numbers, the next step is to calculate the dispersion. So here is the definition of dispersion, and I'm just putting this normalization here. And interestingly, at least it was it's not surprising, but I was surprised when I found the result by the first time, because the dispersion of the populations is nothing but the predictability, which is a known quantity from quantum optics since the 80s. Okay, so predictability is nothing but the variance of the populations, except by a constant. Okay, what about coherences? The absolute value of coherences. Again, the average is nothing but the L1 norm of coherence that I have shown you. Okay, now the number of terms is, you have D times D, D2 minus the diagonal, so D2 minus D. Okay, so this is the average. And then when you have the dispersion, you get to a quantity that I wasn't able to find anywhere. So this is going to be the object of this talk. So I call this the coherence dispersion for obvious reasons. And it depends on that L1 norm of coherence. This is the so-called L2 norm of coherence. It's not exactly a norm, but it's the use of the term. And it's like this, but with a square here, okay? So this is the dispersion of coherence. Okay, so we can summarize all this in this simple table where you have populations, absolute values of coherences, average, variance, and you have 1 over D, the squared predictability, L1 norm of coherence, and there was this missing slot that is the coherence dispersion. Okay, what does it tell us? And this is partly what I'm going to discuss with you from now on. Okay, some properties. Note that any qubit state has 0 coherence dispersion because you have a single coherence. There's no dispersion. So this quantity is 0 for the simplest possible states, okay? And coherence dispersion vanishes. Let me just like this. So this one is one element of the computational basis, and this F is the balanced sum of all basis vectors, okay? So coherence dispersion vanishes for this state, of course, because this state is incoherent, but it also vanishes for this state because it is completely uniform. It has all coherences, but they all equal to 1 over D, so there is no dispersion. Okay, so you can have high coherence, but 0 dispersion, of course. On the other hand, the relative entropy of coherence also vanishes for this state, but it is maximized for this state. Okay, this is going to be important. This is the reason why I'm stressing this. Also very important, this quantity can be shown to be convex. Okay? Okay. So here is this state 1. It has 0 coherence dispersion and 0 entropy of coherence. And here is the balanced superposition. It has also 0 coherence dispersion, but maximal entropy. Okay, and this is just a interpolation. It doesn't matter much what are those coefficients. It's not important. I just for x equals to 0, a is equals to 1, and those are 0. And for x equals to 1, we get this. Okay. So I interpolate between these two, and I get something like this. Well, this is quite interesting because, okay, for now it is a specific example, but anyone who worked with complex systems, not anyone, but many, would be aware that there is a kind of institution in this field called complexity entropy diagrams. Okay, And okay, this is basically some entropy in the x-axis, and some quantity that translates some feature of complexity. Okay, and there is a prevalent signature of this kind of diagram across several fields. You can find text complexity, linguistics, complex systems in general, biology, and so on. Okay, and the prevalent feature is this: is that you have a maximum complexity for intermediate entropy. And sometimes we take entropy as being a synonymous to complexity, and this is not true, right? For instance, here you have no complexity and no entropy. But here you have maximum entropy, but this is not very complex, right? Whatever the idea of complexity you have, this is not exactly what complex means. And here we have something that is not maximally entropic, but is much more complex. Okay? And as I said, this is very general. There are several fields in which you find this kind of diagram. For instance, those papers that I'm showing, they are more or less classic of this field, distinguishing noise from chaos. The noise and chaotic system may have the same entropy, but not the same complexity. Of course, what complexity means and entropy means varies from subfield to subfield. Complexity and adaptation, and this is, I found this interesting. They have recorded the sounds of the rainforest and then analyzed this kind of diagram. And you see that the shape is not constrained, but just this general feature. You have an entropy, you have a complexity, and you have an intermediate maximum. It's more or less like this. There is a dual relationship between complexity and entropy. Okay, so back to our plot, which of course in this case it is specific of that interpolation, so I cannot make any general claims. But soon I'll be able to do this, because convexity tells us that the state that maximizes this quantity must be pure. Okay, so I set to calculate these maximally complex states, if you will. It took me a few months, but I will explain you in 2 minutes. It's not complicated, it's not complex. So the states are something like this, but not full rank. Okay, the states that maximize this coherence dispersion, they have a rank that is smaller than the dimension. So you can make some optimization. I mean, my optimization is paper and pen. Okay, no computer, and using Lagrange multipliers, and you get this very cute little equation, but it has a tree here, and so the solution is ugly. Okay, but the fact is that there is a single solution, so a single maximum, and it's a complicated function of the dimension. Of course, I took this as a real variable, so to finally find the optimal rank, I have to take this function. I can explain in more detail if you want. So for instance, for dimension 3 and 4, the optimal rank is 2. For dimension 10, it is 4. For dimension 100, it is 17. Okay? And here is how it varies. Okay, So now I have shown that the states that maximize complexity or coherence dispersion have intermediate entropy. Those are the ones that maximize entropy. Okay, so indeed I have this peak here for intermediate entropy. Okay, so this is a kind of robust behavior of this quantity. So I am saying that, I am claiming that it has a flavor of complexity. Okay, and okay, so this is the first ingredient. And if I am talking about complexity, it would be nice to be able to analyze a bunch of subsystems. Okay, so one can use this complementarity relation. This is that L2 norm. This is the quantity that I already mentioned, the squared predictability. This is purity, trace of rho 2, rho squared. Okay, so you can replace C2 here by these other quantities, and this is useful because the other quantities are easy to scale. So they are easy to determine for an arbitrary number of copies. So with this, I can determine the coherence dispersion of an arbitrary number of subsystems. And note that it's not necessary that all the states are exactly the same, because I am always talking about the absolute values of the coherences. So if the states differ by local phase and also shuffling of the base elements, this still applies. Okay, so I have now this possibility to address a huge number of subsystems, which reminds me of thermodynamics. Okay, just a comment before that. I told you that the simplest states have they have zero coherence dispersion, but this can be superactivated. If you take 2, it is in general already non-zero. Okay. So as I told you, I would like now to investigate what I can say if I assume that there is a thermal bath surrounding this big system with a lot of subsystems. Okay, if I have thermal equilibrium, this is boring because the thermal state has no coherences, and this is zero. And also, even if I have a classical state outside equilibrium with some athermality, it is also zero. I mean, if you only take deviations from the Maxwell-Boltzmann statistics, but you keep the state diagonal, this is still zero. So, in a sense, to address an interesting situation, I need some coherence. Okay, and arguably one of the important thermodynamical states that has coherence is this coherent Gibbs state. And this state is nice because it has only quantum athermality, in the sense that all diagonal elements comply with the Maxwell-Boltzmann distribution exactly. Okay? So I will use this state, but of course, saying that you have this pure state in an open system is quite a contrived hypothesis. And so, in fact, I will assume that I have a lot of thermal equilibrium with some remnant coherence. Okay, so this lambda may be quite small. Okay, I have more or less 10 minutes. Okay, 5 plus 5. It's good to know that right now. I will speed it up. Okay, so with this, you can calculate the coherence dispersion of an arbitrary number of systems in that state. It all boils down to getting the purity of the thermal state. Okay, so the coherence dispersion of this athermal state is can be written in terms of the purity of the equilibration state, but at 2 different temperatures. This is just a signature of non-equilibrium. And I will make a further assumption, which is that our system will have a single relevant energy scale. So I will consider D-level system where you have to jump the same amount of energy to get excited. In this case, the purity is given by this, where tau is this dimensionless temperature that takes into account the energy scale. Okay. Okay. If you take n equals to 1, this is boring. This is something like this. Now this is temperature, right? Temperature. So it just starts at 0. Everyone is in the fundamental state, so it's that state, and then it saturates. But interestingly, as soon as you make n equals to 10, 1,000, 100,000, 1 million, you get this behavior. It is 0 everywhere except around a very specific temperature. And this, well, I was curious about this. What does this temperature mean? Okay. Okay. So far we have complexity, and I tried to find a system where we congregate all these features, all right? So complexity, this system that I'm going to talk about is out of equilibrium par excellence. Coherence is conjectured to play some role in specific processes, and there is a universal energy currency. Anyone? What is this system? Okay. There are some microscopic processes in life that have all this, because life is, of course, complex. If you are completely equilibrated with the environment, I'm sorry, but you are dead. And coherence, some remnant coherence is conjectured to play roles in photosynthesis and avian compass and other biological systems. And there is a universal energy currency, which is the energy that you get when you break an ATP molecule and get an ADP molecule plus this 0.3 electron volt of energy. Algae, fungi, bacteria, any living being in this planet uses this quantum of energy, okay? So my system is going to be something like that. This is the cell. This is the physicist cell. And I will skip everything but energetics, okay? So I will assume that there are many points within the cell that can that need to use energy, okay? What is the energy? I'm not going to be specific. It might be to unfold a molecule, to make a transport of against a gradient. Okay, so those are active if they are being used, if they have the energy of an ATP, inactive, and for a few of them, I will assume that can be a coherent superposition. Okay, so I have the energy scale, but I need n in that formula, and I don't know if it is 1,000, millions, or billions. I know that I am about to. Okay, but I will use 2 or 3. Okay, then I had to make a search on the literature, and luckily I found this PNAS that gives you the feeling for numbers in biology, and there is also this initiative, BioNumbers, hosted by Harvard, and yes, the number of ATP molecules inside a E. coli bacterium at any time is about is of the order of millions. Okay, and also it reproduces in this temperature window. So I use those inputs, and of course I asked me, okay, could that peak be associated with this window of temperature? And in principle, the answer is yes, because if you take this temperature and transform it to that dimensionalized scale, it's 0.3 to 0.35. And if you look what are the n that you need to use in the formula to get the peak in this interval, n is between 50,000 and 300,000, which is between 2 and 10% of the total number of ATP. So it may not be clear now, but if you change a little bit the energy scale, this would be completely off target. Okay? Well, but E. coli is a very specific living organism. I decided to vary wildly those parameters. So I took 1 order of magnitude below, 1 order of magnitude above. So I varied n about 3 orders of magnitude. The level of coherence can be very, very low. And the dimension doesn't matter if you use 1 ATP or 20 ATP. The only thing that is fixed is here. And when you vary those parameters in these very broad intervals, the maximum drifts from this to this, which corresponds to this temperature scale, which interestingly is almost the same as this interval, which is the interval where life is recorded to exist on Earth. Okay, so you may vary those parameters a lot, but this will not change much. So it's kind of interesting. On the other hand, if, and this is my last slide, if you just take a factor of 2 here, the temperature window goes to a region where it is incompatible with life. So it is very sensitive to this one. Okay, this one is fine-tuned. And okay, that's it. Thank you.
So we have time for 1, maybe 2 questions.
Thanks for the wonderful talk. I enjoyed it a lot. The delta C is the coherence, but physically, can you give me a physical meaning for the for this? Yeah. For instance, in the ATP, ADP process.
Yeah, I mean, it is related to coherence, but it's not exactly coherence in the sense that I explained. And I think it gives you a notion of complexity. So in the ATP, ADP conversion, what is apparent is that if you have the system described by that Gibbs state, coherent Gibbs state, this figure of merit for complexity is maximized exactly in the interval where life occurs. This is all I can say. No claims.
Okay, thanks.
Okay.
Well, let's thank Fernando again, and we have a coffee break soon. So if you have more questions,
Thank you.